Thanks, Christopher. Also, thanks the previous presenters in our session. Many of the concepts I need were already covered. So my name is Mingfu. We are from Penn State University, and well, I talk about proceeding work about seeding. So seeds in sequence analysis are often referred to short and fixed length features of long sequence. Transforming long sequences into regular seeds are beneficial because efficient data structures such as deep-learning graph, Bloom filter, and hash tables and algorithms can be applied. So let me briefly mention a few existing seeding methods among many others. So perhaps the simplest ones are k-mers, as this example showed here. So k-mers often combined with the sketching methods such as minimizers to reduce the number of seeds. So we just learned species that are k-mers combined with don't care positions, and also Stromer developed by Christopher that use multiple windows, and in those windows, minimizers can be picked jointly. So let's see 3 applications of seeding. Number 1, read mapping. So we can extract seeds and then collect seed matches. A seed match is a pair of identical seeds. And this seed match indicates a potential mapping location of this read so that we can extend on both directions to find a statistically significant alignment. Number 2, sequence alignment. Again, we can extract seeds and collect seed matches, and then find a subset of the collinear seed matches so that a score function can be optimized. Number 3, overlap detection. So we are given a large set of sequences or reads, for example, 1 million long reads, and we aim for identifying all overlapping pairs. Of course, we want to avoid all versus all comparison. So a practical approach would be to use seeds. We can extract seeds for individual reads and only examine pairs that admit seed matches. And for those potential overlapping pairs, we can use a fine-grained approach such as chaining to determine if they are truly overlap or not. So what would be a good seeding approach? So in principle, we hope a seeding method to be highly sensitive. That is, for similar sequences, for like biological related sequence, we hope more seed matches will be produced. At the same time, we hope a seeding method to have low false positive rate. That is, on these similar sequences, fewer or hopefully 0 seed match will be produced by the seeding method. So in light of this, we can see that k-mers are good enough for sequencing data with low error rate, evident by both the theoretical analysis and many successful tools that we use every day. However, k-mers are greatly challenged by sequencing data with high error rate. We argue that k-mers cannot achieve both high sensitivity and low false positive rate. So to see this, consider if we use a large K, then we can hardly find any seed match even on similar sequences. This is because a single edit can break K continuous k-mers. Like in this example, we only have 2 edits, but the 2 sequences don't share any k-mer for K is 5 or above. We can switch to small k, but then these similar unrelated sequences will also share many seeds. So what can we do? So the key issue here is that similar sequences don't share long k-mers when the error rate is high. Then what do they share? They share long subsequence. Like in the same example, X and Y share a subsequence of length 12 as indicated by this optimal alignment. In fact, 2 length n sequences with a added distance of E will guarantee to share a subsequence of length n minus E. So we use this sk of X to indicate the set of subsequences of length k of X, and same for Y. And then we can use the Jaccard index to measure the similarity of the 2 sets of subsequences. So here I give the Jaccard index for 3 k values to give you some idea. Like when k is 11, you can see X and Y share 12 length 11 subsequences. And the Jaccard between the 2 sets is 0.087. So it's quite a small number. So inspired this observation that similar sequence share long subsequence, we propose our new CD method called subseq hash. Subseq hash is pi of x is a function that maps the length n string x to its smallest subsequence of length k according to pi, which is order over all the length k strings. So to visualize, this is again the set of all the subsequences of length k of x, and each pi of x will map x to the smallest one. And this smallest subsequence is also called the seed of x, defined by subseq hash. You may find this definition similar to minimizer. Actually, they are. Minimizer picks the smallest substring, smallest chimera in the window, and subseq hash picks the smallest subsequence. That's the difference between them. So then one question, how to calculate subseq hash? How to find the smallest subsequence? By definition, of course, we can enumerate all the subsequences and then pick the smallest one according to the order, but then this certainly takes exponential time because the number of subsequences grows exponentially. To find a better solution, let's dig into the properties of subseq hash. In fact, the secret is in the orders. So the order pi balances the probability of seed match and the computational hardness. So let me explain. Consider a random order to the left. So a random order looks like this, like all the length key strings are shuffled. Then the probability of hash clearing, the probability that x and y will be hashed to the same seed is exactly the G card according to the property of min hash. And this is a nice property. But we don't know how to calculate the smallest subsequence if pi is random. We think it's hard. On the other hand, consider a lexicographic order. A lexicographic order looks like this. It's very regular. Then for lexicographic order, the smallest subsequence can be computed very efficiently in linear time. But the probability of hash clearing gets much reduced. So you can see now the two orders are desirable because we want a fast algorithm, of course, but also we want a higher probability of hash clearing. So actually, we have a solution that can achieve both. So we design a specific order, not random, not lexicographic order, but some other order over all the length k strings. And we show that a polynomial time algorithm can be designed under this particular order pi. And we also show experimentally that the probability of hash clearing is close to the G card. So let's see the order. We call it ABC order. It is determined by an integer parameter d and 3 random tables A, B, and C. So table A is of size k times d times the size of alphabet, and this is what table A looks like. So each entry is a random number. It's a random real number. Table B is of size with the same with table A, but each entry is a pair. It's like +1 -1 pair. Table C is size of k times the size of the alphabet, and each entry is picked randomly from 0 to d-1. So once you choose those entries randomly, then the order will be fixed over all the length k strings. So because the table defines a score for each length k string z, and the score is a pair, f and g, both are defined recursively. To define order, so we first compare f. If they have the same f, then we compare their g. So here I have an example. So for this length k string z, its score is for -200 or something, calculated following exactly this recurrence. So why would we do that? What's the intuition behind designing such an order? So there are two reasons. The first, we use this modulo operation and the +1 -1 to shuffle the length k strings so that the order behaves like a random order so that a higher probability can be achieved. The other reason is both f and g are recursively defined. That is, up to position I, the score only depends on the previous score at position I -1 plus something above the current position. And because of that, a dynamic programming algorithm can be designed to calculate the smallest subsequence, simply because the score is recursively defined. And the time complexity for calculating the smallest subsequence for a single length n string is big O of n times k times d. So we use simulation to estimate the probability of hash clearance. So we simulated a bunch of strings of length 20 and grouped them by their edge distances, showed x-axis here. And for each pair, we will apply a seeding method, either a minimizer or subseq hash, to get a seed of length 16. And we'll check if the two strings in a pair are hashed to the same thing or not. And we use the frequency of a seed match to estimate the probability of hash clearance. So let's see the top line. So the top line corresponds to subseq hash with random order. Again, according to the property, we know that this gives the G-card, estimates the G-card similarity. The next three lines gives the result of subseq hash combined with the ABC order. And you can see they are very close to the G-card, especially when D is 11 or D is 31. The bottom two lines corresponds to the results of minimizers and subseq hash combined with the lexicographic order. You can see they have lower probability of hash clearance. Another observation from this figure is that the probability of hash clearance is quite low. Let's see, like when there are two eddies or three eddies among like a pair of length 20 strings. So when there are two eddies, although subseq hash with ABC order gives a higher probability, but it's still quite low, like under 10%. When there are three eddies, the probability is about 3-4%. So to increase the probability of hash clearance, to increase the chance of having a seed match, we can simply repeat. Let's say like repeat subseq hash 10 times, each with a random independent set of ABC tables. And then X length n string will be mapped into 10 seeds, same for Y. And the probability of having at least one seed match becomes 1 minus p to the power of 10, where p is the probability of hash clearance with a single subseq hash. We emphasize that repeating is very effective for subseq hash, simply because p is like strictly positive most of the time. Remember, like X and Y will guarantee to share a length k subsequence if k is less than or equal to n minus e. So most of the case p's will be strictly positive, although it's small, but it can be boosted by repeating. However, minimizers like repeating are not effective for minimizer, simply because most of the time p will be 0. So if X and Y don't share any chimer, which can easily happen when the error rate is high, then p is 0, and repeating will not help. So let me show you some result to show that subseq hash can give better seed matches for the three mentioned applications. So this, pay attention to this dotted black line. It corresponds to the results of using all the chimers. And those four nearby solid lines corresponds to subseq hash without repeating. And those four lines corresponds to subseq hash repeating 10 times. And you can see they give much better results than all chimers, minimizers, and subseq hash without repeating. I'm sorry, I forgot to mention the setup of the experiment. So it's for like sequence alignment. We simulate a bunch of strings of length 100,000 with the error rate of 10%. And then different seeding methods will be applied and the seed matches will be collected. So the x-axis gives the coverage of the correct seed matches. So the larger the better. The y-axis gives the coverage of incorrect seed matches. So the smaller the better. So the lines to the right are better methods. So for risk mapping application, we get similar results and similar conclusion. So for overlap detection, we see a seeding method would predict a pair as overlapping if they share at least one seed match. And therefore, we can calculate the precision and recall of different seeding methods. So Those lines correspond to all keymer's and minimizers, and those lines on top, which are better, corresponds to subseq hash with the ABC order. And note that this sort of best line corresponds to quite large n, that is n is 60. And this particular point corresponds to n is 60 and k is 48. All right. To summarize, we propose subseq hash that use the smallest subsequence as seed. And to make it practical, we design a new order, ABC order, and design an algorithm that can calculate the smallest subsequence and this order in polynomial time. And we show experimentally that the probability of hash clearance is close to the Descartes. So we propose this new seeding scheme for data with high error rate. We suggest to use subseq hash with large n and large k. For example, like n is 30, 40, even 50, 60, depending on the applications. And we suggest to use a large k, a k that is close to n. For example, like 80% of n or 90% of n. The reason to do this is to reduce false positive rate. Think about if two like quite long length n strings are mapped to the same quite long subsequence, then this must be a true pair. And to increase sensitivity, we can simply repeat. And we believe that this approach can achieve both high sensitivity and low false positive rate. And this is something cannot achieved by keymer's, as we argued previously. So I would conclude with thanking the talented co-authors in my group, Xiang, Qian, and Ke, and the funding agencies, NSF and NIH. And thanks everyone for your attention.
Okay, we have time for a quick question. Yes.
Hey, this is really cool. I'm very excited. But I do have one quick sort of comment and then a follow-up question. So your justification here is that a k-mer, like a single SNP change is going to affect k-mers, but isn't it also going to affect k subsequences of size k?
Yes.
So,
yes.
So that I don't know if I quite get the justification, but it seems to work. But the question is, you propose a new ordering. Did you use the same ordering for your minimizer scheme, or did you use random?
For minimizer, I think we use a random order. Yeah, random order is used for minimizers.
So you didn't test the difference, whether the ordering or the thing is better?
Well, we tested also included the random order for the subseq hash, which is the best. Yeah. Back to your first question, yes, like a single edit can affect subsequences significantly, of course, but the difference is like there exist shared subsequence, but there exist of them, and we can boost them through repeating.
I was just wondering how practical it is in terms of like memory and like runtime. Like, would this scale to full human genome?
Yeah, great question. So it's not practical yet. So we are like 10 times to 200 times slower than minimizer, but seeding is usually not the most time-consuming step in sequence comparison. So we care about the quality of the produced seed matches. So as you can see from the applications, so either sequence mapping or alignment or overlap detection, they all rely on the seed matches rather than seeds.